Well, hello, everybody, whoever's in the audience today. And my name's Andy Rivenes. I'm a product manager with Oracle for database and memory. And I have the privilege today of being able to co-present with David Kurtz of Go Faster Consultancy. So our goal was to describe database and memory, kind of how it works, what the base level feature is, and then how David's been able to use the base level feature for a couple of customers for general ledger reporting. So I think that's going to be pretty exciting. And the base level feature is something that we've introduced to allow folks to use database and memory without first having to license it. So my contact information's there along with David's and our Twitter and blogs. I'll probably mention our blog, the Oracle blog for InMemory during the presentation, and I have a couple slides at the end. One of the things is our resources page, where if anybody wants to find more information about database and memory, they can go there, and we have lots of links there to help you get started. So with that, I think we'll continue on. Oh, well, maybe, there we go. Get the focus there. So why use database and memory? So database and memory, it's not a one-size-fits-all option or feature of Oracle database. It's really focused on improving existing reporting performance. In addition to that, something I think is even more exciting, being able to do real-time analytics or real-time analytic queries on your operational data without first having to wait for that data to be ETL'd to a data warehouse, or maybe extracted and put on a reporting system. You can actually run it right on your source data, if you will. In addition to that, reduced overhead. So not only do we not use analytic reporting indexes, which folks have typically had to put on to their applications, and the overhead associated with keeping those analytic reporting indexes up to date, the space they take, the undo and redo generation. But in addition to that, since we're running our analytic queries in memory much faster, we typically use less resources to run those existing reporting queries. So we get kind of a double benefit there. So reduced overhead or reduced workload, if you will, being able to run analytics in real time right on your operational data. And then anywhere you have current reporting requirements, since it's part of database memory, is part of Oracle database, you don't have to change any of your applications. So you can literally run with just enabling database memory and populating objects in the column store, which we'll talk about. So what is database and memory? Typically, actually, Oracle's traditionally been a row formatted database, great for OLTP or transactions. But since the data is all associated in rows, to do analytics, you have to look through a lot of data in order to get to the column values that you're typically interested in for analytic queries. Hence, creating analytic reporting indexes to try to speed that up. Columnar-based data, columnar formats, great for analytics. You only have to look at the columns you're interested in your queries, tends to compress and vectorize well, but it's not very good for analytic or OLTP, because you have to basically reassociate those column values back into rows in order to run your transactions against it. And that can be fairly expensive to do, something we call stitching the columns back together. And that's there's a lot of overhead there. So columnar formatted databases aren't very good for OLTP. Now with database and memory, we have a dual format. So Oracle database is a row formatted. All of the data still exists in the row format, but you get to pick and choose objects to populate in columnar format, typically the ones that you're doing your analytic reporting against that have business critical importance. Since it is in memory, it's much, much faster, but the data always exists in the row store as well. So we haven't changed the Oracle database architecture per se, we've just added the ability to have columnar formatted data in memory, which makes it much faster. OLTP transactions still occur in the row format. We haven't changed that. Basically what we do is we keep the column store simultaneously and transactionally consistent with the row store. We do metadata updates. I'll talk a little bit about that, but you always get a reconsistent view of your data. So there's never a chance that you'll have data out of sync. Think of it as this kind of analogous to keeping indexes up to date during OLTP processing. Although since there's no persistence for the data in the column store, it's much faster since it's in memory, and we don't have to generate, undo, or redo to keep the a consistent view of it, because if the database or this instance was to go down, when it comes back up, we just repopulate that data from the row store back into the column store. The advantage here is that all of your existing Oracle technology still works. Anything from active data guard and your recovery to all of the current features that you have with Oracle database. Nothing is prevented from being used with database in memory. In fact, and I'll talk a little bit about this, some of the features actually are enhanced with database in memory, and as we leverage those features to be able to do even more with database in memory. And I guess I kind of mentioned that already, but again, the big thing is no application changes are required. So it's an optimizer decision based on cost to access data either in the row store or in the column store. Very simple to implement database in memory. So there's one initialization parameter, in-memory underscore size. You set that, we allocate the column store, the in-memory area in the SGA, and then that's it. And then all you have to do is alter tables, partitions. We support sub-partitions and materialized views to be enabled for in-memory, just a simple alter table command. And then later, you can perhaps drop analytic reporting indexes, those that are no longer being used because now you're doing a table access in memory full, you're accessing that data in the column store. And since we don't use or access indexes, then you perhaps can save disk space, undo, redo generation, and overhead of keeping those indexes up to date, as I mentioned. So how does database in memory work? So it's a pure columnar format. We populate data once you've enabled it with those alter table commands. We populate the data asynchronously in the background in a pure columnar format. We compress that data, so you typically get anywhere from a 2x to a 20x compression rate. Wouldn't be Oracle if we didn't have a lot of options, and so you have multiple values that you can set for compression level. By default, we do mem compress for query low, which typically gets you at least a 2x compression rate. You can go higher than that. So if you have, say, 500 gigabytes of data that you want to populate in the column store, it's not going to take 500 gigabytes of memory to do that. Since a lot of our Oracle customers tend to run fairly memory tight, if you will, in their database servers, that can be a big advantage. You don't have to populate the entire database in a column store. It's not a in-memory database from the standpoint that you have to put all of your data in memory. You get to pick and choose the objects that make sense for your analytic workload. It's available on all hardware platforms. So you don't have to have Exadata. Anywhere Oracle database runs or database in memory can run. And we introduced, I guess I should mention, we introduced database in memory in 12.102. So any version 12.102 or higher has database in memory already built into it. So then it's just a matter of setting the in-memory size parameter, enabling objects, and away you go. It's very, very simple to implement. When we do allocate the in-memory underscore size parameter or allocate the in-memory area, it's allocated out of the SGA. So we haven't changed the Oracle database architecture. We leverage what we've already built in the past. But one of the things I say is don't steal memory. So the in-memory part of this is adding additional memory to your database server. You don't want to steal memory from, say, the buffer cache or the shared pool, because your existing workload is likely to suffer. What we're really talking about is adding additional memory to the in-memory area to populate those objects to significantly speed up your analytic workload without impacting your OLTP workload. So that way, kind of a mixed workload environment, you can actually then, as I mentioned earlier, run analytics right on your operational data. It's just the in-memory underscore size parameter we allocate out of the SGA. So obviously the SGA has to be large enough to handle that, whether it's SGA target or whether you're doing manually allocated memory pools, you just need to factor that in. And then in the in-memory area, it's made up of two pools. You see this in some of the $V views, like $V in-memory area. We allocate a 1 megabyte pool and a 64K pool. Basically, you don't need to know any of that other than it's helpful to know how full the column store is and how many objects you've populated. We place IMCUs in the 1 meg pool or in-memory compression units. That's the actual columnar data. Then we have metadata. We keep track of any changes that occur to data in the row store. We keep track of that so that you always get a consistent view in the column store, and those are in the 64K pool. A little bit, I think, more clearer, easier to understand, I think, a way to look at this is that when you populate an object, it's going to be made up of one or more IMCUs or in-memory compression units. And I should stop and say that I've done blog posts, Ask Tom, office hours sessions, and obviously in the documentation, we describe how all of this works under the cover. So if you have interest in learning a little bit more about this, there's definitely information about that. But an object will be populated in the column store, and it'll be made up of one or more IMCUs, each of those IMCUs will then be made up of one or more of these 1 megabyte extents I mentioned. And then each IMCU will have an SMU, or the metadata unit, and it'll be made up of one or more 64K extents out of the 64K pool. And so together, that's basically how an object's populated in the column store. And then population, as I mentioned, is an asynchronous background process. You can alter the priority of population so that you can populate certain objects before other objects. Once an object's populated, though, the priority doesn't make any difference in the sense that we don't access certain objects with higher priority before we access other objects. It's just really a population control mechanism. Populations done by background processes or a W processes. You can see I put a red circle around a top session there. Bottom line is you can adjust the number of processes that do population. So for instance, if at database startup, you want to get all of the data populated in the column store before you let applications access that data, because perhaps you don't want anyone querying the data and not having the data in memory because it'll be slower, so it will kind of affect your SLAs. You can bump those populate server processes up so that you can dedicate the database server to populating data in the column store. And then once the data is populated, you can go ahead and turn your applications loose. So we give you a few knobs to control things, because it wouldn't be Oracle if we didn't give you choices. But with that gives you the ability to control that. However, I will mention that the database will still start up and operate normally. So we don't prevent, database in-memory doesn't prevent the Oracle database from opening. Once we've allocated the column store as just part of the SGA creation, the database is up and available, and then you can determine how you want to populate your objects in the column store to serve your application workload requirements. And then let's talk a little bit about the base level feature, because that's what David's going to talk about in a little bit. So with 21C, we added what we call the base level feature to database in-memory. This allows you to allocate up to 16 gigabytes of column store without having to license the database in-memory option. So the idea here was to kind of show the value of database in-memory. Presumably you would want to license the database in-memory option, but you don't have to. If 16 gigabytes works for your application, then that's perfectly fine to use. We actually backported this to 19C, starting with the 19.8 release update. So if you're on 19.8 or higher, or in 21C in the future, you can actually make use of database in-memory without having to license it, which is pretty cool to be able to try out database in-memory, or even maybe for limited use, as David will talk about, with certain applications, being able to use that without having to pay extra the full database in-memory license for it. What we wind up doing is you set an in-memory _ force parameter to base level. we limit you to being able to allocate just 16 gigabytes of column store. You can obviously allocate less if you want. And what this does then is changes the way feature tracking works so that none of the licensed folks will come down and talk to you about using the option because you're using the free part of database and memory. Not a lot different than the ability to use up to 3 PDBs with multi-tenant. So the advantage here, though, is that it works with rack, so you can actually scale out database and memory with the base level feature and use up to 16 gigabytes per rack instance. And then in a CDB environment, you can allocate the 16 gigabytes to a CDB, and then each of your PDBs can use up to the total of the CDB's 16 gigabytes. And so basically that allows you to make use of database and memory, again, without having to license the option. There's only a few exclusions, only a few things that you can't do. By default, or with the base level feature, you only get the default compression level, which is mem compressed for query low. So typically about, well, there's my dog, about a 2x compression level. You can't exclude columns. You can only, sorry, little distraction there. You can you have to populate the entire table. AIM isn't enabled, and the cell memory feature on Exadata is not usable. So on Exadata with database and memory, you can actually use flash in the cell in smart flash cache for database and memory formats. We call that cell memory. And on the base level feature, that's disabled. So let's talk a little bit about the database and memory technology. So database and memory, columnar format, you only have to access the columns you're interested in. That data tends to compress well. We have different levels of compression. We support in-memory storage indexes, so we can actually prune out data and not have to look at all of the data in that for those particular columns, assuming that they fall outside of the range of your filter predicates. So it's possible that we can skip over certain data so we don't have to look at or scan IMCUs that don't have data in them. And then SIMD vector processing, single instruction, multiple data, allows us to essentially do array processing or scan and compare values, multiple values at the same time. This allows us to go from scanning millions of rows per second per core to billions of rows per second per core. Well, the dog's gone, so that'll be, well, I don't know if we'll be able to edit that out, but, and then the optimizer is also aware of database and memory. So the choice of accessing data in the row store or the column store is a cost-based decision. So the optimizer is aware of objects that are populated in the column store. And then in addition to that, it can choose, or it will push filter predicates and function-based aggregations like mins and maxes into the scan of the data, during the scan of the data. So I usually tell folks that the fastest in-memory query is one where all of the work for that query is done during the scanning of the data in the column store. In addition to that, so we support hash joins with database and memory in the sense that we can turn a hash join into a scan and filter operation. Using Bloom filters, we can actually perform the hash join during the scan of the data rather than having to go back and to the PGA and probe the join table or the probe table in the PGA as we would with a normal hash join. Significant performance improvement. And then we support something called in-memory aggregation, or what you would see in an execution plan, a vector group by, which allows us not only do the join in memory, but also allows us to do the group by aggregation in memory. So that gives us another 6 to 8x performance improvement. So the optimizer in conjunction with the in-memory technology can actually make your analytic queries run much, much faster. I usually tell folks that I'm disappointed if we don't get at least a 10x performance improvement for your analytic queries. So why not just cache the table in the buffer cache? I mean, if we put it in memory, it's in the buffer cache in the, say, the keep pool, which is usually where I do my examples, and this is one of them, wouldn't it be just as fast? And so the answer is no. The columnar format, so in memory is what I like to call an enabler. The columnar format and what we have enhanced with the columnar format as far as the technology and the optimizer features make that a 10x performance improvement or better. And so even if the data is fully cached in the buffer cache in row format, it's still nowhere near as fast as the data being accessed in columnar format in memory. And I have an example here of querying the line order table, doing a max of the total order price. When we query it from in the column store, table access in memory full, it's like 100th of a second. And then the same exact query, the same exact data, just fully cached in the buffer cache. Notice the no in memory hint. It's over 8 seconds. And so you can try this out as well. We have a Live Labs environment, or you can download a VirtualBox or try it in your environment, load up the SSB schema, line order table, or perhaps your own data, and try this out. It's very simple to set an in-memory hint, or a no in-memory hint, excuse me, on your queries, or you can set it to session level, or you can kind of one of the best practices when you're looking at POCs or implementations is to first time your data or time your queries with in-memory not enabled, then enable in memory and rerun that same workload and then make the comparison. One of the advantages doing that is that then, because once in memory is enabled, you can do things like vector group by, even if the data isn't fully populated in the column store. To get an apples to apples comparison, we typically like to say, don't have in memory enabled, run your baseline, if you will, and then enable in memory, and you can run that data again and see the performance benefit. How might you know what queries will benefit from database in memory? What I like to say to folks is, for a non-trivial, in other words, if you're only looking for 1 or 2 rows of data or values, typically an index is going to be the most efficient way to access that data. That's kind of the OLTP part of your application. But if you're doing analytic queries, so you're looking for a non-trivial amount of rows, spending a significant amount of time in execution time, then if you're in your execution plan, if most of your time is spent either accessing data, joining data, or aggregating data, group by aggregations, then database in memory is probably going to make a significant performance improvement for your applications. But you do need, so with that, you do need to target the right workloads. So as I mentioned, we're not going to speed up inserts, updates, and deletes, DML activity. We're not going to help you with network round trips, SQLnet message from client, logons, logoffs, PL SQL code, row by row processing. That's not really where database in memory is going to help. Database in memory is going to help you with your access of your data in the column store. And so again, if you're spending the majority of your time accessing data, joining, or aggregating data, that's where database in memory is going to help your performance. So it is, people, again, it's database in memory is not a one size fits all option. And so that's kind of one of the things that we do have problems with folks making sure they understand, that it's really focused on analytic reporting performance. Does it work with other database features? So it does. With Exadata, we actually have some unique features with database in memory. I mentioned cell memory, or the ability to use flash, which Exadata machines have terabytes of flash. We can actually use, once database in memory is enabled, we can use the flash as like a secondary storage for columnar formatted data. So that effectively gives you terabytes of columnar formatted data available for your analytic queries. Now, the flash won't be as fast as in memory, but together they work and provide you with a much larger columnar memory footprint than if you just had memory alone. We also support in-memory duplication or fault tolerance, in-memory active data guard. So if you had a standby database on Exadata, you could actually run and populate the standby database column store with data and actually run your analytic reporting against the standby database, which folks like to be able to do. In addition to that, we support multi-tenant, which in 21C is a good thing since you only have a multi-tenant environment. So the CDB, as I mentioned, will have the column store, and then each of the PDBs can access that data. With the BaseLevel feature, 16 gigabytes, with the regular database and memory option, basically as much data as or memory as you can put in your database server, since Oracle database is only limited by the memory footprint of your database server. And then we support Data Guard, as I mentioned, Golden Gate. All of the existing Oracle technology you've invested in works with database and memory, so you're not You don't have to turn anything off. As a matter of fact, we leverage RAC for scale out, parallel query to make our in-memory queries even faster. We work in conjunction with everything. We don't affect your backup architecture at all. So it works with RMAN or whatever, however you're doing your backups. And so we don't prevent you from using any of the existing Oracle technology you've invested in. And with that, I'll just mention, we do have a lot of information about how to get started with database memory, everything from a one-pager to a very detailed implementation guidelines. All of this is available on our blog. So I have both blogs.oracle.com in-memory, which is the view on the left, and then our resources page, which is on the right, where I have links to documentation, our Ask Tom office hours sessions, the implementation guidelines, and our Live Labs environment. So if you want to try out database and memory for yourself in our Live Labs environment on the cloud, you can do that as well. And with that, I think, David, I'll turn it over to you and let you talk about how you've been able to use the base level feature.
I've seen all of these presentations about in-memory, and I thought, well, could we make it used for us? Is this just a try before you buy and test? Or could you actually use it for real? I think you can actually use it for real if you've got the right kind of application that fits some of the restrictions that base level places upon you. That's me. Every presentation has heard my slide. This is all about performance, let's be honest. It happens to be about PeopleSoft, but PeopleSoft is not relevant to what we're doing. I believe this is far more generic. It just happens to be I'm taking two PeopleSoft environments as my examples. What is General Ledger? It is a data warehouse of financial facts. You've got all of your OLTP stuff posting to the ledger. Every time you do a transaction, you post 2 entries to your ledger. And then there's big data warehouse style reporting, particularly at month end. And they like to do it on the OLTP database because at month end, they want to put adjustments through and see the consequences immediately. So each entry, each row in the ledger is a fact. It has an amount. It might be in several currencies. And there will be dimensions. There will be time, fiscal year, accounting period. And then there is a whole raft of other dimensions. And not everyone uses each dimension. And in PeopleSoft, you've got these chart fields 1 to 3, which are custom dimensions, which are some attribute of your business, and they can be different from client to client, user to user. And in PeopleSoft, one of the favorite ways is a thing called Envision, which is a sort of plug-in to Excel, and it does these big data warehouse style queries where it's classic data warehouse matrix. You've got various attributes which are held in hierarchies, and you say which bit of the hierarchy in each dimension am I interested in, and it joins them all together and it spreads them out in a report, and you get an Excel sheet, which is your report. 2 clients I'm going to talk about, neither of which chose to let me mention them by name. If I mention them by name, you would recognize them. Certainly the bank you'd know, and certainly the insurance company would be known in the US. They're both running the same version of financials on the same version of People Tools. The insurance company, I think nowadays is on 9. They might have upgraded to 1910. The bank's on 1911. They're both on engineered systems. The insurance company has a 4-year-old supercluster. The bank has a shiny new Exadata. This means that actually there's a bit of a difference in the memory footprint. On the supercluster, we've only got 192 gig per node. On the Exadata, we've got 4 times that. So we've got oodles of memory there. The insurance company is in production with BaseLevel. They were a very good fit for this. At the bank, it's not quite as obvious that it's going to be beneficial, and I'll talk a little bit more about that. The key thing that the insurance company are doing is summary ledgers. They are pre-aggregating their ledger data into reporting ledgers. And this is done by the application, and the application calls it summary ledgers. It's an awful lot like a materialized view, and they're doing an incremental update of it every day. We have, because it's supercluster, we put hybrid columnar compression into quite a lot of things. Most of the historical ledger is hybrid columnar compressed. Summary ledgers, I can't hybrid columnar compress because of the update nature of the incremental process. So we've created materialized views on the summary ledgers without any indexes, which are fast refreshed every day, and they are hybrid columnar compressed. So that was done 4 years ago, and it's very much, we're going to full scan, Bloom filter, hash join these guys in order to get the reports out. We've only got 16 gig of memory per node to play with. That's all there is. They're not licensed for memory, so we're going to allocate 16 gig, and that's all there is to it. At the insurance company, I actually had a bit of a battle to grow the SGA. In the end, they let me grow it by 8 gig, and we stole 8 gig from the buffer cache. In order to keep it fair, we set minimum values for buffer cache and shared pool, because the nature of PeopleSoft, left to itself, Oracle will grow the shared pool. So we quite often set minima to control it. At the bank, they've got about the same volume of ledger data over more years. We've got lots more memory, and we've got 3 rack nodes, which means I've got 3 times 16 gig to play with. But I don't have summary ledgers. So my ledger data is actually quite big compared to the summary ledgers at the insurance company. And I think that's quite critical. We chose to put the summary ledgers into InMemory, not all of them, but some parts of them. All these guys, I should say, are partitioned. I don't really believe you're going to be effective with InMemory without partitioning, because you've got to pick and choose which partitions are going to go into InMemory, and with only 16 gig to play with, you're going to have to be quite parsimonious. You're really going to have to pick and choose where the IO, where the activity is in your database. But we really did deliver a clear benefit. It's actually more than an hour. I went back through the numbers. We think we're taking about 3 hours out of an 11-hour batch. And that's end-to-end elapsed time, not database time. The database time is much greater than that. And what this means is, well, what they wanted was they wanted to deliver the report package, which runs every night, because this is an insurance company, and they love to slice and dice their data in every which way to value their business every day. They want to deliver this suite of reports onto people's desks at the start of the working day, US East Coast. What we've been able to do is to do that start of the working day, continental Europe. So they love this. It's made a massive, massive difference. So we've done it we've partitioned our ledgers and summary ledgers by fiscal year and accounting period, and they've got multiple ledgers, and they've got adjustment ledgers as well. So we've sub-partitioned it on ledger, so we can pick the specific bits of data out with partition elimination. And then we were getting very good performance in 12.1 with hybrid-columnar compression, and now we're doing even better by layering InMemory over the top of that. But we're picking and choosing which fiscal years on which summary ledgers we're doing that to, and if we haven't got enough InMemory, well, we'll revert to the hybrid columnar compression, full scan, Bloom filter there. There was no way we were going to squeeze ledger and ledger budge into InMemory. It was just too big. So we didn't even try. It's only the summary ledgers, which they have fewer analysis columns, so they have fewer rows, so they're smaller, so we can squeeze more in. And we've got 4 or 5 summary ledgers and a couple of the materialized views, and most of them have got 2 fiscal years. They've got current and previous fiscal year in memory. Anything else, we'll go back to doing it in the old-fashioned way. You can only have 16 gig in your base level. How much you're going to allocate? Let's be honest, you're going to allocate all of it. There's just no argument. There's no point allocating less than 16 gigs. You would not, as Andy said, you would not steal memory from the SGA. And if you do, you're going to have to be quite careful. We got away with stealing 8 gig of buffer cache, but your mileage may vary. We had to decrease the minimum value on the buffer cache by 8 gig to release it. We also upped the shared pool by 2 gig. That's probably more to do with the 12 to 19 upgrade. It probably doesn't have a lot to do with it memory. At the bank, it's absolutely no problem. We've got lots of memory. So we slap the 16 gig in. I would love to prove to these guys that this is effective, and they should put their hand in their pocket and say, look, let's have 200 gig of InMemory. And I should say, I am not on commission from Oracle Corp. But so
you'd quite like to be for that.
I wish. But, I think that's a valid proof of concept. We could get some benefit in production and say, look, guys, I think you could get more if you licensed it so that I can put the rest of your 768 gig into InMemory. It's a good, what else are you going to do with it? So what did we do? We set InMemory force base level. That keeps us legal. We set InMemory size to 16 gig. We grow the SGA by 16 gig. We set InMemory optimized arithmetic enabled. That was a big advantage. What that does is it additionally holds the numeric columns in a different format that is easier to process in things like sums. So if you're doing select sum from summary ledger where group by, that sum executes much quicker. Now, the penalty is it takes more space because it's held in the standard format and the in-memory optimized format. So you're giving up a bit of your in-memory store, but it's worth it. The juice is worth the squeeze. The other thing is the in-memory store, that 16 gig is divided. It's divided between the 1 meg and the 64K. And some papers say 20%. We've seen 30% allocated to the 64K pool every time. I've done this in several environments at both clients. Well, that's a lot of memory to lose from your 1 meg pool where your data is actually stored. And what we observe is, in fact, that the 64K pool is very lightly used. I should say that the summary ledgers are relatively static. There is a one-time daily update, and then they're pretty static. In fact, they are static during the reporting run. So you haven't got dynamic data. It's not like you've got processes posting to the ledger. Have had processes posting to the ledger. At the bank, we've also set in-memory trickle % to a higher value. It defaults to 1%. We've been a little more aggressive about pushing the data in there. Andy will not approve of this, but what we've done, and this is in capital letters, so this is undocumented. It's not recommended by Oracle. You'll notice this part of the presentation is not on an Oracle slide deck. This is me talking, not Andy. What we have done is we have cut back the 64K pool to 10%. What this has done is it's given me 3.2 gig per rack instance. That's worth having. Usual caveat, it's an undocumented parameter.
David, can I interrupt just for a second? So we recently created a MOS note. So if you call Oracle support, you can get them to tell you, what's going on here. And we're considering making this a real parameter. So based on your and other customers' experiences, we're responding to that. So it's not super secret. It's just it is undocumented, or it is an underscore parameter is what I should say. So your mileage will vary. So
the insurance company, we run off the materialized views. We tried with the in-memory advisor. It wasn't very successful for us on PeopleSoft, but then PeopleSoft has an awful lot of objects in it. So what I did is I analyzed the ASH data and said, what is the sort of IO per gigabyte of the segments which are candidates for this? And take the segments with the highest IO and work down that list and fill your in-memory, because that's the best bang for your bucks. When we did this at the bank, Ledger was the only option. And I managed to squeeze 3, possibly 4 years of ledger data into their 3 times 16 gig. And all you have to do is set in-memory or no in-memory on the segments. What we have is a PL SQL procedure, which does that, because every year we're going to roll that forward to the new fiscal year. So it's going to have to be, we do it programmatically, because next year they're going to have to move it forward. And it's going to be a regular maintenance process along with adding the partitions for the new fiscal years. At the insurance company, we use parallel force local equals false. We discovered that rather than have 2 in-memory pools, which were different, 16 plus 16, we got better performance by having 1 duplicated pool, and we can duplicate it because it's on supercluster. And rather than identify a second 16 gig of segments, we were better off actually sticking with the first 16 gig, but setting parallel force local I don't know why this is true. I suspect this may be to do with the performance of the interconnect, but I don't know. All I know is we've tested it backwards and forwards several times, and we are better forcing parallel force local at the insurance company. At the bank, there's no way we're doing this because I need the 3 times 16 gig. So it depends. We've discovered that sometimes the segments do not distribute evenly across the nodes. So, one node fills up while the other one is still empty. And we think probably the answer to that is distribute by service and round robining them or hashing them across the nodes by service. And we'll do that in the same PL/SQL package that allocates the in-memory, no in-memory attribute. Distribute for service name, whatever. We're not in production with this at the bank, and we're still testing it because we haven't yet put it in conjunction with hybrid columnar compression. That's coming. We cannot prove yet that we're seeing enough benefit within memory. And that may be because it's less good a fit because it doesn't have the pre-summarization of the data. And so the concentration of IO isn't as good in that top 16 gig or top 48 gig, I should say, of IO. So it's an unfinished work in progress. But I suspect the pre-aggregation of the data, which is a very old-fashioned, data warehouse technique to reduce your IO, means that it's also been a good fit for in-memory. We're not doing that at the bank. Yeah. So watch this space. I may do this again in the future. So what was our tests at the insurance company? We ran this test every night in our test system. It's great. I've got lots of numbers. That is a database time ash graph of the batch that runs overnight. There are different parts of it in different colors. We've got a little bit of a parallel query queuing problem as well. And it runs from 6:41 p.m. till 5:44 in the morning. Okay, we are actually meeting the SLA. It's delivered before the user requires. Within memory, with duplicate, with parallel force local, it finished, you can't see because it's behind Andy's picture, but it finishes at about 2:30 in the morning. It's 4 hours earlier. And I've had to squeeze the graphics so that they're to scale. You can see that there's just less area, there's less DB time, and it finishes sooner. And the peak has gone from 140 down to 120. And there's also a little bit of resource manager to stop the queuing in there, which probably is responsible for half an hour to an hour. And the rest is in memory. It shouldn't be a surprise that your CPU comes down, but of course, if it was all in memory, if it was all CPU before, and now it's in memory and it's still in CPU, it has to be executing fewer instructions. And that's what in-memory does. So we've still got this long tail because we've got a couple of problem reports which are just not written terribly well. We'll have to fight them differently. And there's an extra little bit of S-base in the test on the right, which was running, which is not in the baseline test on the left. But you just have to look at the different shape and the way the load comes down sooner. That means we're delivering stuff to the business sooner. And it's all over way before they come into the office. Most of that win was from in-memory. Very little of it was from other tuning.
Yeah. So that one was, it was parallel queries of the 80 session. It was
on the left.
Yeah.
So on the left is our baseline, and it
all parallel query. I don't remember. Sorry.
Some of them are parallel query, some of them are not. Some of it is capped by resource manager, some of it is not. We adjusted the resource manager to control some of the queuing that ran away with itself. The real result is that we took database time out of this, and the queuing is less severe because the service time is down, and the whole thing just finishes sooner. The total runtime goes down. All the numbers move in the right direction.
We're out of time.
We are out of time, and that is the end of the presentation.
Cool. That's really good.
Thank you.
Thank you very much, Andy.
Thank you, Andy.
Thank you.
No, thank you guys. Thank you very much.
Thanks very much. And
have a good rest of your conference.
Indeed, but I need to get this camera to somebody else.